So hi, welcome to the course of signal processing for millimeter wave communication for 5G and beyond. And this is a problem solving session. So first of all, I just introduce myself. I am Shubhadeep Mondal from IIT Kharagpur from GSNL School of Telecommunication, and I am here to help you for the previous session questions and answers and all these things. So feel free if you have any query about all these things. So may I start the session right now? Hello?
Yes, sir.
Yeah. So this was the previous run's questions and answers. So let us start from the question number 1. And the question is, suppose there is a ultra wideband signal which has a center frequency of 79 gigahertz and the bandwidth was of 4 gigahertz. Then the question is, the channel gain is typically always highest at 79 gigahertz, highest at 77 gigahertz, highest at 81 gigahertz, and remains same through the bandwidth. So let us solve this problem. So what is the path loss formula as described in the described in the actual videos? So this is like freeze path loss formula that comes. And it is equal to that power received by power transmitted equal to GR GD lambda by 4 pi d square. So, and we also know that wavelength, that is lambda, and f is the frequency, equal to speed of light. These two equation is a well-known equation. So the first thing we consider here, what happens if lambda increases? F decreases from this equation number 2, and if f increases, lambda decreases from equation number 2. So what is our point here? It is 79 gigahertz to 4 gigahertz band. So let us solve the question more. Suppose this is the starting band of 79 gigahertz and this is 4 gigahertz. So as per the equation, the question says, the center frequency was 79 gigahertz and bandwidth was 4 gigahertz. So it will be stretched from 79 to 81 and 77 gigahertz, right? So let me draw once more it. This is 79 gigahertz and probably the signal spectrum is like this. This is 77 and this is 81. Now the question is, in which frequency you guys think the gain will be higher. Can anyone comment on this? Any approach you guys want to solve it? Anybody here? Okay, let me solve it. So for 77 gigahertz, the frequency is the minimum frequency here. So lambda will be max for this, right? So for 77 gigahertz, lambda is the maximum between this whole bandwidth, 77 to 81 gigahertz. Now let us come to the Friis-Path loss equation. This PR by PT, that power received by power transmitted, depends on the lambda, and lambda is maximum for 77 gigahertz, right? So what will be the answer for it? The channel gain will be highest at 77 gigahertz, because at 77 gigahertz has the highest lambda, and which highest lambda is there is the power is the more, right? So correct option is option B here. So anyone has any query about this question?
One second.
Yeah, pardon? Okay. Let's go to the question number 2. So what this question number 2 implies? This says during signal reconstruction of the signal by interpolation method at the receiver, the bandwidth of the signal increases, decreases, initially increases and decreases and does not change. Show. This is the transmitter side antenna, and this is the receiver. So signal is transmitted from the transmitter to receiver. Now what we do in the receiver side after receiving it in the RF domain, we just send it to the ADC, right? So the signal bandwidth is only in the transmitter side. And it cannot be affected by this receiver. The only thing that can happen, if the ADC rate is very low, then the signal is lost. And this is as per Nyquist criterion. So signal bandwidth cannot be changed. It can be lost, but it cannot be changed here. So which will be the right answer? It does not change. So the correct option is option D. Anybody has any doubt here? Am I audible to others?
Yes, sir.
Okay. So nobody has any doubt, right? Okay.
No, sir.
So that here is the question number 3. So question number 3 is a little bit tricky. The question is like this: suppose a signal can be perfectly reconstructed by Nyquist frequency of 20 MHz, and assume the guard band among the symbols are 2 MHz. So signal cannot be reconstructed when? So let us solve this question. So let me draw the frequency first. So what is mentioned here? The Nyquist frequency is 20 MHz. This is the Nyquist sampling rate. So what is the signal bandwidth? This is 10 MHz. I am talking in the baseband sense here. So it will be like this. Suppose this is 10 MHz signal. And it is mentioned that the guard band is 2 MHz. So probably this is the guard band here and this is the guard band here. So total guard band is 2 MHz. So 1 MHz will be distributed here. Another 1 MHz will be distributed here. So this is 11 MHz. And this is minus 11 MHz, this point. So now, so can anybody comment about, so if I want this type of band, what should be the ADC sampling rate? Anybody here? Nobody here?
So 10.5 megahertz.
Probably no. The answer is, so because the ADC, I am talking about the Nyquist rate is 20 megahertz, right? That is the sampling frequency. At least you need to be. Otherwise, this 10 megahertz signal cannot be reconstructed, right? So this is 20 megahertz. The Nyquist rate is 20 megahertz. That it mentioned here. But there is excess 1 megahertz also there. And here 1 megahertz. So total is 22 megahertz. So ADC sampling rate should be 22 megahertz, such that this 20 megahertz is there and this total is 22 megahertz. This is 20 and the total is 22. So let me draw it again. So let me draw the spectrum again. This is in the baseband. This is pi 2 minus pi. and this is the maximum frequency, and it corresponds to 11 megahertz, as the guard band is 2 megahertz, and the signal is from 10 megahertz to minus 10 megahertz. Minus 10, 10. So now we want to downsample this, and the question is asked if I, or upsampling I can also do. So first is downsampling, I think. Let us discuss the term for downsampling, how it works. So the highest frequency is 11 megahertz, and now the question is, if we downsample it at the order of 10 by 11, so what it comes? The highest frequency is 11 megahertz, and I multiply it by 10 by 11th order, as I am downsampling by 10 by 11th order, so it becomes 10 megahertz. So now how the spectrum works? This is minus pi to pi. But what this pi is right now, what is the maximum frequency in the baseband case?
11 megahertz.
Tell me.
10, right?
This is 10. Yes, right now it becomes 10. This is minus 10 mega, corresponds to minus 10 megahertz, and this is 10 megahertz. And what was the actual bandwidth of the signal? Nyquist rate was 20 megahertz, so signal bandwidth was 10 megahertz. So if I downsample it more, greater than this factor 10 by 11, what will happen? This signal will be aliased with the other part, like more than this, then the aliasing will come here. So this aliasing, if this aliasing happens, we cannot reconstruct the signal again, right? This is the case I am telling about. So signal cannot be reconstructed if this downsampling is greater than 10 by 11 order. This is the answer, as we discussed, like the whole thing. So what will be the right answer here? Option A. So the next question. Oh, anybody has any doubt about the previous question?
I think in this question they have asked about frequency. Means options are like this.
Where?
If it is greater than or less than 0.5 megahertz. It's not, order is not mentioned over.
Okay.
Then
I know the actual
time
question.
will be-
I know the actual question.
Yeah.
And I made the TA, but the question should be modified. You can note down this question if you want. Like there was something wrong in the question of previous semester. Pardon for that. So about this question, you have any doubt, like, or you have any doubt about the previous question? Like that was not possible. I know the question was wrong. Is it fine with you?
No, I don't understand what you are trying to say.
Like the previous question was wrong. Whatever is described in the Nptel portal, that is wrong. The question is wrong.
So what we supposed to do?
That is
Okay, anyway.
anyway.
Okay, fine.
Do you have any doubt about this question?
No.
Okay,
No,
thank
sir,
you.
it's clear.
Yeah, fine. Like previous question was about ISI also. Like we cannot comment anything about ISI from this frequency spectrum also, right? Like aliasing is happening here, but aliasing does not guarantee anything about ISI. So the next question is for frequency flat fading channel, the number of channel taps is what?
One.
Yeah, it is 1. So the reason is like let me describe. So can anybody comment when frequency flat fading channel can happen? What is the condition for frequency flat fading channel?
When simple time is greater than channel coherence time.
You cannot comment like that. Like it is frequency flat fading channel. What does that mean?
Sorry, the multipaths are very less. Or
Multipaths are very less. That can be. Take frequency flat fading channel means let me take like this is the flat channel, and whatever the bandwidth here. So frequency is affecting all the frequency with the same amplitude, right?
Channel bandwidth more than the data bandwidth.
Yeah, that is the case. Suppose this is the data bandwidth for you. This channel bandwidth is more than this. This is also the case for frequency flat fading channel. So here why it cannot be 2 in the case? I am telling you. Only the reason I want to find out. The options were like, right? If someone told like it is 1. Why not 2? Why not 3? 2 on 3 and also very less number of channels, right? Channel taps here. So let me describe. Suppose there is only one channel tap. So this is the transmitter side and this is the receiver. And one channel tap, there could be 2 conditions only. One condition, there is no reflector here, like in a free field, a big field, we are communicating with each other and there is no reflector. At that case there could be a direct communication, and that is delta of t minus the propagation time, that is delta t minus tau. Another thing can happen, suppose the same condition repeats and there is only one reflector, so it comes here and it goes there. There is also delta t minus tau. So this is the channel response here. So if there is, so what is the Fourier transform of delta t minus tau? Can anybody comment? In the frequency domain, how will see it?
flat.
So this will be flat, right? Fourier transform of this function. Like what is the Fourier transform of delta pulse? It contains all the frequency components, right? I think you are getting this.
Yes, sir.
Okay. So if I add anything, one more delta of t minus something 2 tau, So this corresponds to another pulse, right? Here is one delta, another pulse delta, and then we add up all these things. It will not preserve the frequency flat sharing thing if there are more multiple taps here, like another tap here, a long distance here. This will distort this flat frequency spectrum. Like phase will come in this sense. All the components will not be affected by the same thing. So the right answer here is, if only one pulse is here, only one single path of propagation is there, then only it will be a frequency flat fading channel. So please, if anybody has any doubt, you can ask me. Okay, I guess nobody has no doubt. So the question number 5 here. What does the question number 5 tells? There are different time delay in a channel given by 1 microsecond, 2 microsecond, 5 microsecond, 8 microsecond. This is the same case like I discussed in the previous question. Like why the delay comes here. So this is the transmitter and this is the receiver. So probably there is a line of sight communication, and this take 1 microsecond to reach. Another is very large path and it is going here, so it takes 8 microsecond. In the same thing it can be 5 microsecond, all these things. So as a result there will be channel taps. So 3 dB coherence bandwidth, how it is calculated? So 3 dB coherence bandwidth, that corresponds to this is CB. What is the formula of this? CB is equal to 1 by 2 into tau max. So tau max is the maximum delay. So CB is 1 by because 8 microsecond was the maximum here. Time delay here it was, and this is from the term 10 to the power 6. I divide it like 10 cube and 10 cube. This comes because 8 microsecond was there, so I convert it into the second, so it comes like 10 to the power 6 by 2 into 10 to the power 8. I simplify it again, I forgot to simplify. So this becomes 62.5 kilohertz. So the correct answer is 62.5 kilohertz here. If anybody has any doubt, they can ask me the question. The next question. By increasing the RF from 6 GHz to 200 GHz within a fixed distance communication channel, which of the following phenomena is the most appropriate? So let me solve this problem. So first equation here, lambda, this is lambda and this is frequency is equal to speed of light. This is the first equation. So for 6 GHz, what happens? For 6 GHz, what is the lambda? That is my first point. So lambda becomes C by F with 3 into 10 to the power 8 by 6 into 10 to the power 9. This is 5 centimeter. However, now calculate the wavelength for 200 GHz. Now for 200 GHz, what is lambda? 3 into 10 to the power 8, as it is the speed of light, into 200 into 10 to the power 9. This is in gigahertz, that is the reason 10 to the power 9 is here. So this becomes 1.5 1.5 millimeter. So for 200 gigahertz it is 1.5 millimeter. For 6 gigahertz it is 5 centimeter. Now see this wavelength, this is equivalent to a lot of small particles, and the small particles will start to act like the scatterers in high frequency. So this is the main problem for millimeter wave communication. Like this very small frequency, very high frequency, for very high frequency, the wavelength becomes comparable. Wavelength becomes very much comparable with the small particles of the nature. That creates the scattering effect. This creates scattering. So what was the question? Let me go first there. It is like 6 gigahertz to 200 gigahertz, and the distance was also fixed for the communication channel. So the right option will be option B, like the number of scatterers will increase, because I am going to 6 gigahertz, that is in centimeter, to 200 gigahertz, the wavelength becomes in millimeter wave. So the right option is option B. So number 7, how the small scale fading is related to. The first option is constructive and destructive interference of multipath signal paths between transmitter and receiver system. It is independent of the frequency of the signal. That is the second option. And that third option is take place at spatial scale of the order of the carrier wavelength, and D is both A and C. So let me comment how the small scale fading happens here. The small scale fading this has many reasons. Let me tell the reasons what can be. Like, as I told previously, if I take a very long bandwidth here, that is wideband model, not the narrowband model, this is the wideband model. Then what happens? The gain of the channel becomes dependent on frequency and this, as I discussed earlier, this scattering event starts so this cannot be independent of the frequency of the signal, but option A is constructive and destructive interference of multiple signal paths between transmitter and receiver system. That means there are a lot of reflectors in the environment and they are adding up, or that makes constructive and destructive interference, right? There are reflectors in the system, in the environment, and they will create the multiple effect, multipath effect here. And this is also in the carrier wavelength. Like, carrier wavelength depends on the frequency. If I increase the frequency, the small particles of the nature that will start to scatter the actual transmitted signal. So the small scale fading will be related to both A and C. So the right answer will be the correct answer will be option D. So let us go to the next question. So this is the question 8. What does question 8 refers? This says, in wireless channel, the frequency dependence of individual attenuations and propagation delay may be neglected for first wideband channel, narrowband channel, ultra wideband and terahertz channel. So let me solve this question again. Again, for this question, lambda nu equal to c. Nu is the frequency and lambda is the wavelength. And c is the speed of light. So terahertz thing, that cannot be answered, because in terahertz frequency is very high, and that makes small particles as scatterer. So what are the other options here? Wideband channel, narrowband channel, ultra wideband channel. So only for narrowband channel. The reason is here like this. If the model is wideband, this frequency gap is huge. That is true for wideband and ultra wideband in both the case. And this gain, that means channel gain, this becomes dependent on the frequency term, lambda and f both. That is also so only for narrowband. So this is the case for the wideband scenario here. So frequency dependence on individual attenuation and propagation delay may be neglected for what? It can be only done for narrowband channel, because for wideband channel and ultra wideband channel it is dependent on the channel gain is dependent on the frequency. And for terahertz channel, what happens? The scatterers comes into the picture and it start to just deteriorate the channel at terahertz model. So only the narrowband channel model you can neglect these individual attenuations and propagation delays. So correct option is option B. So anybody has any query about all these things till now?
Sir, can you please repeat the eighth one?
8-1,
How
right?
it-
8-1.
Yes, narrowband.
So you
Yes,
have
please.
any query about 8-1, like where you did not understand this point? Okay, let me try once again. The question is like this. It is frequency, and I am sending in the bands here like this. So the question is, when this frequency will not be affected by particular this frequency. Like, see, probably this is 79 gigahertz and this is 100 gigahertz. So what will be the channel gain here? At 79 gigahertz it will be maximum, like the function will be like this. Because why? Because there is a freeze path equation, right? GDGR, and that depends on lambda by 4 pi d square. So at here lambda will be maximum, so this frequency will have high gain. And this frequency will have low gain. So the gain of the channel that is attenuation here. In the question it is attenuation here. The gain can be renamed as attenuation in the wireless channel. So here will be low gain and here will be high gain. So this gain is dependent on the frequency, individual frequency terms. That is true for any wideband channel model, right? So the question is, the wireless channel, the frequency dependence on individual attenuations and propagation delays may be neglected. So if it is wideband channel or ultra wideband channel, the individual attenuation of the particular frequency components will come into play because of the freeze path loss equation. And for terahertz channel, what happens? As I discussed earlier, the small environment particles will act like scatterer. So there will be frequency dependence on this. The more the frequency, the smaller particles comes into the picture of the attenuation factor. But if it is narrowband channel, what happens if it is narrowband channel? Narrowband channel means this will be very narrow with respect to the center frequency. Like if this frequency is 79 gigahertz, this will be 79.5 gigahertz. So this 0.5 gigahertz band, this is very narrow, and gain will be almost independent of the frequency factor in the small range, because it is very small region. That is the reason this narrowband model, the individual attenuation will not come into the factor for narrowband channel model. Is it clear right now?
Yes, sir. Thank you.
Okay.
Sir,
Yeah, tell me.
sir, this terahertz channel,
Yes,
it
yes.
can also be wideband or narrowband, right?
Yes, this can be. Terahertz channel can be. That is the reason. Like in the sub 6 gigahertz, the spectrum is almost full here, right? So we are exploiting all this millimeter wave. Millimeter wave means gigahertz, 60 gigahertz, 79 gigahertz, all these things. And terahertz is also possible. Terahertz means it can be used in the indoor systems, like indoor Wi-Fi type of things.
Okay, sir. So in that case, if it is terahertz narrowband channel, then also we can neglect the frequency dependence, right? Of the reflector.
Yes, that is the play. Like you have to select how much frequency spectrum you are thinking of. But if you are thinking of terahertz, you have to think what is the wavelength of that thing, right?
Right, sir.
Like if the wavelength is so small, like small scatterers will create the path delay here, right? There is a point mentioned like propagation delay. Every scatterer will contribute some path delay because they are like any small dust particles. Every dust particles, they will come into the picture for terahertz. That does not come in the gigahertz, 6 gigahertz, but if it is 6 terahertz, at that moment those small particles comes into the play, right?
Right, sir.
So that may be the case. That is why we are neglecting this terahertz channel. Like, I cannot comment. You have to model on that thing, and you have to see what happens, because in terahertz everything, a lot of things comes into the play. Is it clear now?
Okay, sir.
Yeah.
Yes, sir.
So this is a very straightforward question. The delay spread is 10 microsecond. What is the coherence time? So this coherence time is equal to 2.5 into delay spread. So what is the delay spread here? 10 millisecond. 2.5 into 10, and this is 25 millisecond. This is the answer. So answer A. The right answer is option A. So this is the last question. Probably this question is not discussed in the actual videos right now, still now, but still I am discussing this thing. Let me admit some. So what is the question here? We have to find the incorrect one here. This is the coherence time and WC is the coherence bandwidth here. And the question is, flat fading happens when WC greater than W, delay requirement is greater than coherence time, TC is the coherence time, and slow fading happens when TC is greater than delay requirement, and frequency selective fading happens when WC is greater than W, that is signal bandwidth, and WC is the coherence bandwidth. So what will be the answer according to you? Anyone here?
D.
D, why?
Sir, if W is less than coherence bandwidth, then it will be frequency flat fading.
Yes. In that sense you can say, right? So the frequency selective nature of the spectrum will be gone, like as I discussed earlier. That is the reason the option D will be the correct answer here. Like, let me discuss also it. So probably this is the signal bandwidth, and it is saying that this channel bandwidth is more than this, like coherence bandwidth. This is WC. So in this case, for this region, what is the frequency response here? It is almost flat here for the channel bandwidth, right? But this WC, if this WC so this will be the right answer for frequency selective fading, right? Is it clear to everyone? Okay, fine. So, anybody else has any question about all these things, like all the question I discussed earlier, or anything about the topic that is going to be discussed in the next week also?
Sir, could you go to question number 5?
Okay, yeah, I can go. This is
Sir, why you have taken 8 microseconds?
because 8 microsecond. You see, what we should consider here, like this is the maximum. I am telling you. Like here is one tap, second tap, third tap, and this is it. But this is 8 microsecond. So I have to take the consideration of this 8 microsecond also. Like this is the maximum delay that can happen. Right, of the from the transmitter side to the receiver side, the maximum delay that can happen is 8 microsecond. Now, if I think about the frequency response of this channel, like highest time difference is 8 microsecond. I have to take consideration of this highest time delay, right? Like if the like all the signals comes like this. So let's take this part takes the highest time, 8 microsecond. So this signal will reach in the last, like it will reach first, after that probably this will reach to at and this is 5 microsecond probably, after that this reach, and after that this reach here. So I have to take the consideration of the highest term here, 8 microsecond, and it will give me what is the coherence bandwidth, 3 dB coherence bandwidth. According to that I have to set the coherence bandwidth, right? Because 8 microsecond is the highest delay that happens in the total system. So that's why the equation is like this, as I discussed here, that coherence bandwidth is 1 by 2 into tau max, because what is the maximum time it requires to transmit the signal from transmitter to receiver. So that depends on the coherence bandwidth.
But sir has taken tau d as a maximum of difference of tau I minus tau j. So whatever
Yes.
is the maximum difference, that is what sir said. And now you have taken the maximum value. So I'm a bit confused.
No, see, that is happens when, like I am saying, that is, you can also consider that fact. But probably the first pulse is coming at 1 microsecond, right? Not at 0 microsecond, or something more closer to 0. So you can consider about that also. That is also right in that sense. But according to all these options, only 62.5 kilohertz is coming into the fact, right? If you consider anything else, you are getting any of the answers?
No, I think what you have given, sir, that is different from what is we are having in the assignment. So, if I am right now calculating, you are right. One should take 8 microseconds. But there, while I was solving the problem, I have taken the difference, and then what I got is 62.5 kilohertz after taking the difference.
Okay, that is also
So,
true. See this 1 microsecond and 8 microsecond, all these things comes into the factor when, like in the wireless channel, you are thinking of a multi-part reconstruction or destruction in sense of interference, and from all these multi-path things are coming, right? So that can come into the play, that whatever you are telling, it is right. I'll comment like it is right also. But in this case, whoever has said the question, if you calculate according to the options here, like 62.5 kilohertz, 6.25 kilohertz, only option A is coming according to him. I cannot comment on him, but I know probably in the way he has solved this. So sorry for all these things happened to you, like probably some misunderstanding happened. Is it clear till now?
Okay, thank you.
Okay. Then fine. Then for the next solution, we will meet in the next Tuesday. If you guys have any doubt, you can ask me on that day. So today I am leaving the meeting right now.